In this video, we're going to find absolute maxima and minima over a closed interval. So our process for doing that is to first take the derivative of the function and find the critical numbers that are in the interval. That is, the places where the derivative is either 0 or the derivative does not exist. Then evaluate f at each critical number. What is the output of the original function at each critical number? What is the output of each function at the endpoints? And finally, compare these output values, and the absolute maximum is the largest of these values, the absolute minimum is the smallest of these values. So I'd like you to try this for each of the examples below. Find the extreme values for the function over the given interval in each case. H of x is negative 3 times the cube root of x squared over the interval from negative 1 to 1. F of x is e to the x squared minus x over the interval from negative 2 to positive 1. And g of x is x squared over x minus 2 over the interval from negative 2 to positive 6. So pause and try those out, and we'll talk about them together. All right, first one. H of x is negative 3 times the cube root of x squared over the interval from negative 1 to 1. First thing is I'm going to rewrite h of x as negative 3 times x to the 2/3 so that I can take the derivative using the power rule. And then h prime of x, the derivative is negative 3 times, bring the power down, 2/3 x to the 2/3 minus 1 is negative 1/3, and that can be rewritten as, well, the 3 and the 3 cancel out since they're multiplied together. So I've got negative 2 times x to the negative 1/3, and I can rewrite that as negative 2 over x to the 1/3. X to the 1/3 is the cube root of x. So that is h prime of x. So now I have to think about the critical numbers. So those are places where either h prime of x is equal to 0 or h prime of x does not exist. So is h prime of x ever 0? Negative 2 over the cube root of x. Is that ever 0? No, this is never equal to 0. If we have a fractional function, that can only be 0 if the numerator is 0. So negative 2, the numerator is never 0, therefore the entire function is never equal to 0. So there won't be any of these situations in this particular case. What about when the derivative does not exist? So h prime of x is negative 2 over the cube root of x. Are there any situations where this does not exist? Yes, if the denominator is equal to 0. And for us, the denominator is equal to 0 when x equals 0. So when x equals 0, h prime of 0 does not exist. So that means that our only critical number is the point x equals 0. All right, we also need to, so that's our only critical number for this function. We now need to evaluate f at each critical number, or h, and also evaluate h at its endpoints. So h, the original function evaluated at 0, gives us negative 3 times the cube root of 0 squared, and that is 0. Note that h of 0 is defined. If h of the function is not defined at a critical point, then it is not really a critical point because there is no defined value for that function. But h of 0 is defined at this critical value. The function does exist at this point, but the derivative does not. Okay, what about, we want to now, so this is part of part 2, we are evaluating the function at each critical number and at the endpoints. So h of each endpoint, our endpoints were negative 1 and positive 1. So h of the endpoint negative 1, that's negative 3 times the cube root of negative 1 squared. So that's negative 3 times a positive 1. That's just negative 3. And similarly, h of 1 will also be a negative 3 because that negative 1 gets squared and then multiplied by negative 3. And so we've evaluated h, the original function, at each of the critical numbers and endpoints. And now we just need to compare these values. And we see that h of -1 and h of +1 give us our absolute mins. So there are two absolute minimum for this. And h of 0 is 0. That was the largest of all the values. And so this is our absolute max. And if we want to give the entire point for each of those, we see -1, -3, and +1, -3 are our absolute mins, and 0, 0 is our absolute max. Now, if we graphed this function from -1 to +1 over our interval, we would see that yes, these two values are our minima over the interval from -1 to +1. The endpoints are the absolute mins, two absolute mins. And here we've got a cusp at the point 0, 0. Remember that at a cusp or a corner, the derivative does not exist. So our derivative does not exist, and this is our absolute max over the interval. It's also the absolute max for the entire function, but we're just asked over this particular interval. Our next function, f of x equals e to the x squared minus x. So first we are going to, find the derivative, f prime of x, and any critical values or critical numbers. So f prime of x, we're going to need the chain rule here. The derivative of e to the something is e to that something multiplied by the derivative of the inside function. That's 2x minus 1 in this case. So are there any critical values? Again, those would be places where f prime of x equals 0 or f prime of x does not exist. So maybe the easy one first. This never happens in this situation. E to the something is always defined. 2x minus 1 is a polynomial, so it's always defined. No such values in this case. F prime of x, this function is always defined for all possible values of x, so don't have to worry about that. What about when the derivative is equal to 0? So when is it true that e to the x squared minus x times 2x minus 1 equals 0? When does that happen? Well, first of all, this part is always greater than 0. E to the something is always greater than 0. If you look at the graph of e to the x, it will always be a positive value. So that part is never 0. But the other piece that it's multiplied by, that can be 0. So when does that occur? So 2x minus 1 equals 0 implies that 2x is equal to 1, or x equals 1/2. So this is our only critical number, our only critical value. And so now we need to evaluate the original function f at all critical numbers in the interval. Our interval was from -2 to +1, so that is in there. So f of 1/2, the original function evaluated at that point, that is e to the 1/2 squared minus 1/2. That's e to the 1/4 minus 1/2, that's -1/4. And we could also write that as 1 over the 4th root of e. Okay. What else? We need to now, 3, evaluate f at the endpoints. So our endpoints were -2 and +1. F of -2 is e to the -2 squared minus, so that's plus +2 minus the -2. And so that's e to the 4 plus 2, that's e to the 6th. And our other endpoint was 1, so f of 1 is e to the 1 squared minus 1, that's just e to the 0, and anything to the 0 we know is 1. So now we need to compare these values. So compare these outputs from the endpoints and the critical numbers. So this is clearly the largest value. E to the 6 is bigger than 1. E to the 6 is 2.718 times itself 6 times, so it's much larger than 1. And now what about 1 versus 1 over the fourth root of e? Well, the fourth root of e is larger than 1, so 1 over the fourth root of e is the smallest. If you wanted to calculate it, you could, and you would get that this is approximately 0.779. So you can calculate it, or you could just leave it as it is. But this is smaller than 1, it's smaller than e to the 6th, so it's the smallest of the values. And therefore, that means that 1/2 comma 1 over the fourth root of e is the absolute minimum over this interval, and -2 comma e to the 6th is the absolute max over this interval. And if we did graph that function, we would find that we've got the point, here's 1/2 comma e to the -1/4 power. That is actually the absolute max over the whole graph. We haven't shown that, we've only shown that it's true over this particular interval. If we look at the point 1 comma 1, that was one of the endpoints of our interval, we see that that is not a maximum over the interval, because it also goes to -2. And -2 is like way off the charts. It's some really big number, e to the 6th, which is not pictured here. Last one, g of x is x squared over x minus 2 over the interval from -2 to +6. So first, we're going to find g prime. G prime of x is equal to, we need the quotient rule, low x minus 2 d high 2x minus high x squared d low, that's just 1, all over the bottom squared, x minus 2 squared. And since we're going to need to set this equal to 0 and solve for x, we do want to simplify this. So this is equal to 2x times x, that's 2x squared, minus 2 times 2x, that's 4x, minus x squared, all divided by x minus 2 squared. We're going to leave the bottom like that because it's actually more convenient to have it in that factored form. And so this is 2x squared minus x squared, that's just 1x squared, minus 4x divided by x minus 2 squared. So now we want to look at what are the critical values. So we could first look at places where g prime of x does not exist, where the derivative is undefined. And that will occur when the denominator equals 0. So that will occur when x is equal to 2. But is this actually a critical value? Observe that g of 2 also does not exist. So g of x was x squared over x minus 2, and that is a situation where, again, our denominator is equal to 0. So because g is also not defined at 2, x equals 2 is not actually a critical value, because since g of 2 does not exist, because g is not defined at that point, it can't be a maximum, it can't be a minimum, it is undefined. Okay, so there are no situations where g prime of x does not exist for this example. What about situations where g prime of x equals 0? Well, this is a fraction, so the fraction will only equal 0 if the numerator equals 0. So this would be when the numerator, or the top, is equal to 0. And so that's when x squared minus 4x equals 0. We can solve for x, so this would be when x times x minus 4 equals 0, factoring. And that means that either x equals 0 or x equals 4 are going to be the two places where that occurs. Okay, so now we need to, step 2, evaluate the original function g of x at the critical numbers. So our critical numbers were x equals 2 and x equals 4. Where x equals 0 and x equals 4. G of 0 is 0 squared over 0 minus 2. That's 0. G of 4 is 4 squared, that's 16, over 4 minus 2. That would give us 8. Step 3, we need to evaluate the original function, g of x, at the endpoints. So our endpoints were negative 2 and positive 6. G of negative 2 is negative 2 squared over negative 2 minus 2. So that's negative 2 squared is a positive 4 over negative 2 minus 2, negative 4, and that's an output of negative 1. And g of 6 is 6 squared, that's 36, over 6 minus 2, that's 4, so that's an output of 9. Now we need to compare these outputs, compare these values for the output g of x, and what do we see? We see that we've got output of 0, output of 8, output of negative 1, and output of 9. We see that 9 is our maximum, and negative 1 is our minimum. So actually neither of the critical values is an absolute max or min. It so happens that over this interval, the endpoints give us our maximum and minimum. So that means that negative 2 comma negative 1 is our absolute min, and 6 comma 9 is our absolute max, and that's over the interval from negative 2 up to positive 6, over negative 2, positive 6 for this function. If we graph that function, as we see to the right, g of x equals x squared over x minus 2, then one thing that we have is we have an asymptote at x minus 2. We've got this vertical asymptote, and this function is sort of hugging the asymptote on each side. And we see that there is something special happening at each of the points that we found. So at each of our critical values were 0 and 4. So at 4, it was a 4, 8, and a 0, 0. Those were our critical values. And this is a local minimum, or relative minimum, and this is a local max. But the process that we're going through right now only finds the absolute max and absolute min over an interval. And we see that this is not the absolute min over the interval, because, any of these points over the interval are smaller than it. And similarly, this is not an absolute max over the interval, because again, any of these points are smaller than it. So if we'd been over a different interval, like the interval, for example, from negative 2 to 2, then 0, 0 would have been an absolute max over this interval. It's just not over the interval that we're talking about. In future sections, when we look at the first derivative and what it means, we'll be able to use that to find local maxes and mins as well as these absolute maxes and mins.